1,000 years ago, somewhere on this planet, a group of humans looked up at the night sky and saw a pattern. Stars that never moved, lights that drifted slowly, and occasionally, something odd that didn't fit any story they'd been told. Back then, they called it omens, gods, spirits. Today, we might call it something else. A glitch, a hint, a trace that something far smarter than us had already noticed this little blue world and quietly tagged it in their cosmic database. So let's tell a story where three wild ideas collide. First, that advanced aliens may have already found us long ago. Second, that our entire reality is a kind of high-resolution simulation. And third, that the speed of light is not just a cosmic speed limit, but a built-in parameter of that simulation. Then we'll go to the most uncomfortable part. If that's even partly true, what can we possibly do about it as ordinary humans who have to wake up tomorrow, pay bills, and go to work? Start with the old question physicists and astronomers love to poke. If the galaxy is so old, so big, and so full of stars like the sun, where is everybody? The Fermi paradox points out that many sun-like stars are billions of years older than ours, which means that if technological civilizations arise, even occasionally, they've had more than enough time to spread across the Milky Way, send probes, or at least leave obvious megastructures or signals we could see with our telescopes. In other words, by simple timescales, the Earth should have been visited, pinged, or surveyed already many times over. And yet, when astronomers look for clear, unambiguous signs of alien engineering or ships in our solar system, they come back with the same answer. There is no convincing evidence that we've been openly visited by extraterrestrial civilizations. That clash between they should be everywhere and we don't clearly see them anywhere is the tension at the heart of this story. One way to resolve it is to say, maybe they're rare, maybe they self-destruct, maybe they're hiding, maybe we're early, maybe we're boring. But another, more unsettling option is this. The reason we don't see them is not that they aren't here, but that the system we are in is not rendering that part of the story for us. Just like a game engine only loads the level you're in and the objects you're supposed to interact with, our reality might only expose a tiny slice of what's really going on. Before going there, bring in the simulation hypothesis itself. A philosopher framed it as a cold, mathematical argument, not just a sci-fi dream. He said, think of all civilizations that reach the point where they can run enormous, high-fidelity simulations of conscious beings. Either almost none of them ever get that far, or they get there but choose not to run such simulations, or they run so many that simulated minds vastly outnumber biological ones. If that third option is true, then statistically, most beings like us would be simulated, not base level. In his analysis, you end up with a split. Either the probability that such simulations are ever run is extremely small, or it's almost certain that we ourselves are living in one. That argument doesn't tell you which branch is correct, but it forces you to admit that we might be in a simulation is not just a stoner thought experiment. It's a serious possibility you get by combining basic probability with assumptions about future computing power. Later work even spells out that if a civilization avoids self-destruction and gains the resources to simulate entire worlds, the expected number of simulated people could be gigantic compared to the number of biological people who ever lived. In that framework, being simulated becomes the default, not the exception. Then things get even more twisted, because physicists have increasingly started to look at the universe through the lens of information. One researcher has argued that there may be a new law of physics, sometimes called the second law of infodynamics, that links information and entropy in a very particular way. He claims that information-rich systems, like genetic data in DNA, seem to show patterns that look like built-in data optimization and compression, not just random chaos, and that this might hint at an underlying digital structure to reality. In his proposal, if the universe behaves like a huge information processor, it makes sense that it would compress data wherever possible to save on computational cost, exactly like a programmer would when dealing with a massive simulation. He has even suggested a concrete laboratory experiment, measuring the information content of elementary particles by essentially erasing them and observing what remains, an attempt to see whether information behaves like a physical quantity with its own conservation rules. If such an experiment confirmed that information behaves in a specific way, he argues, it could count as empirical support for the idea that the universe is digital at its core, and possibly simulated. That's still controversial, still debated, and certainly not a consensus. But it shows how far the simulation idea has crept from late-night philosophy into peer-reviewed physics papers and proposed experiments. At the same time, other physicists are pushing back hard. Some recent mathematical work has tried to show that the kind of universe we appear to live in, one with deep mathematical structure and non-algorithmic behavior, could never be fully reproduced by any computer, no matter how powerful. Using tools from logic like Gödel's incompleteness theorems, these researchers argue that any simulation is, at its core, a set of algorithms, but the fundamental level of reality exhibits aspects that are not reducible to algorithms. So a perfect simulation of the entire universe is mathematically impossible. In that view, the simulation hypothesis isn't just unlikely, it is ruled out by the way mathematics itself works. On top of that, some within physics have built new mathematical frameworks for thinking about chains of simulations. Worlds simulating worlds, simulating worlds, simulating worlds, and found that even infinite chains are consistent in principle. So you don't automatically get a paradox from who simulated the simulators. That means the argument is not settled by hand-waving. The math says, both, yes, endless levels can be defined, and also, in some formulations, a simulation of everything may be impossible. You end up with a weird split screen, one side building models where simulations are everywhere, the other side constructing proofs that the universe cannot, in fact, be simulated in the total, exact way people often picture. Now drop aliens into this picture. If highly advanced civilizations exist, then in the simulation argument story, they are also candidates for being the simulators. They might have created countless simulated Earth-like worlds and run scenarios. What happens if you seed a planet with early life here, tweak the chemistry there, alter the climate a bit, nudge the asteroid impacts or supernova rates? In that context, aliens found us 1,000 years ago might mean something different from a big ship landing in medieval Europe. It might mean that some higher-level intelligence flagged our branch of the simulation as interesting, turned on a higher logging level around the time our civilization started forming, and began collecting data. Consider how we scan the universe for life today. We talk about technosignatures and biosignatures, radio leakage, atmospheric gases out of equilibrium, infrared excess from giant structures, weird patterns in light curves. To us, those are clues that another civilization might exist. To a simulator, our entire planet is a technosignature, a glowing ball with oxygen, methane, artificial nightlights, and radio emission. In their view, we're that weird speck in the corner of the screen that suddenly started doing interesting things around the year 1000 or so, cities brightening, agriculture spreading, written languages changing the game. Yet, despite how easy it might be for them, they don't show up in clear, cinematic ways. The data we have on UFOs and similar phenomena, when filtered through scientific standards, remains frustrating. Lots of anecdotes, lots of unidentified signals, but no rigorous, repeatable proof of alien ships hovering over major cities and announcing themselves. Some scientific reviews point out that despite decades of searching, we still have no convincing evidence of alien technology in our solar system. That could mean they're not here, or it could mean that if they are, their presence is tuned to stay below the detection threshold of the instruments and theories we have. The way a game designer might hide developer tools behind debug menus only accessible with special codes. Now, bring in the speed of light. In Einstein's relativity, the speed of light in vacuum is the absolute speed limit. Nothing with mass can reach or exceed it, and it governs how cause and effect propagate through space-time. Experiments have hammered on that limit for over a century. Early on, there was a famous interferometer setup that found no ether wind and helped establish that light speed is constant in all directions. Today, we go much further. Modern tests look for tiny deviations from what's called Lorentz invariance, the principle that the laws of physics, including the speed of light, are the same for all observers, no matter their constant velocity. Recently, scientists have used photons that travel billions of years from distant gamma-ray bursts in flaring galaxies to test whether higher energy photons travel slightly faster or slower than lower energy ones. If the speed of light depended on energy, it would show up as tiny arrival time differences after that long journey, a signature of certain quantum gravity models that tweak the structure of space-time itself. The results so far, within the sensitivity of powerful telescopes and careful statistical analysis, no such deviations have been found. That pushes the possible energy scale where any violation could show up far beyond what we can test directly, tightening the bounds by about an order of magnitude and forcing many theories into a tiny corner of parameter space. In simpler words, the cosmic speed limit of light keeps passing brutal exams. In a simulation view, that is intriguing. Any complex simulation has to respect some constraints, bandwidth, latency, update rates. For a cosmic scale simulation, a finite speed of information propagation looks like a natural way to keep things under control. The speed of light could be how fast the underlying server is allowed to send information between distant regions of the simulated space. Just like an online game has a maximum take rate and network latency, our universe may have a hard update speed tied to this constant. That doesn't prove anything, but the fit is psychologically satisfying. A simulation with a finite communication speed feels familiar to our own experience as designers of digital systems. On top of that, theoretical work on the ultimate speed limit for computation shows that there is a maximum rate at which any physical system can perform operations based on fundamental constants like Planck's constant and the speed of light. No matter what hardware you build, classical, quantum, exotic, the basic physics says, for every unit of energy there is a ceiling on how many logical operations per second you can squeeze out. One analysis found that a perfect quantum computer could, in principle, perform vastly more operations per unit energy than current processors, but still can't escape this upper bound, which is as unbreakable as the light speed limit itself. So we have a layered picture. The universe seems to run on strict speed and computation limits. Information behaves more and more like a physical substance. And we have philosophers and physicists arguing that either simulations are everywhere or nowhere. Now mix in the idea that aliens not only exist, but reached a level where they can harness galaxies of energy and matter to run experiments. To them, we might be part of a research project on the emergence of consciousness in a universe with fixed constants. The finite speed of light, the structure of quantum fields, the expansion of space, all of it would be part of the settings file of their simulation. So where does that leave us humans? Walking around inside this possible cosmic sandbox. Are we just NPCs playing out our scripted loops? Or do we have any leverage at all? One thing to notice is that even in the harshest, we're in a simulation stories, the internal rules remain incredibly consistent and rich. The physics we test in particle colliders, the chemistry that drives your brain, the biology that evolved from single-celled organisms. They work as if they are real and law-bound, regardless of whether there's a deeper layer underneath. That means all the usual tools of science, experiments, theories, observations are still our best way to probe whatever the structure is. There are even proposals for how to test whether we're in a simulation, beyond information theory experiments. Some researchers have suggested that if our universe were simulated on a discrete, lattice-like pixels in 3D, then ultra-high energy cosmic rays might show anisotropies or cutoffs that betray the grid underlying space. Others have explored whether certain patterns in quantum measurements, randomness, or cosmic background signals could reveal the fingerprints of a generator algorithm. More recently, some have floated the idea of building our own extremely detailed simulations and then using advanced AI to look for glitches, inconsistencies, or telltale artifacts that might also exist at our level. The idea is almost cheeky. Create a simulation within the simulation and ask a powerful algorithm to learn what simulated looks like, then apply that to our own reality. On the flip side, experiments that attack the simulation idea head-on have found ammunition as well. That mathematical work arguing the universe cannot be simulated uses the deep structure of logic to say, if the fundamental layer of reality involves non-algorithmic aspects, any attempt to capture it with step-by-step computations will always fall short. That doesn't stop small-scale, approximate simulations, but it would kill the dream of a perfect, all-encompassing cosmic emulator matching every detail of our universe. In that scenario, if aliens exist, they are exploring a real, non-simulated cosmos, and we are in it with them, not running on some giant computer. When you bring the Fermi paradox back into this, the story gets even richer. The paradox says, if aliens are around, why don't we see them? One answer is that they are rare or absent. Another is that our methods are primitive. We're like someone dipping a cup into the ocean and declaring there are no fish because none are in the cup. Our sampling depth is low. A third answer is darker. Maybe powerful civilizations expand so fast and so aggressively that if they were in our neighborhood, we'd already be gone. In some Gravi-Aliens models, the typical expansion speed of such civilizations is close to the speed of light, meaning that once they appear in a region of the galaxy, they rapidly dominate it. Under that assumption, the fact that we're still here and uncolonized strongly suggests we're in a rare window before they arrive, or in a safe patch of the galaxy. Now blend that with a simulation angle. If a base-level universe has dangerous, expansionist aliens who spread like wildfire, any simulation of early technological civilizations might end right when those aliens arrive. A simulator interested in our story might freeze or branch the simulation just before the noisy, aggressive kids show up. It would be like pausing a game right before the boss fight, because what the designers care about is not whether you beat the boss, but how you evolved up to that point. Our quiet skies could be not a sign of a silent universe, but of a simulation that has not yet unpaused that part of the script. So what can we actually do, assuming any of this holds even loosely? First, we can accept that whether or not we're in a simulation, the same principles apply. Curiosity, creativity, and cooperation are how we gain more control over our situation. The more we understand about physics, the more we learn about information, entropy, quantum theory, and the structure of space-time, the closer we get to the edges of whatever game we're in. Pushing particles to higher energies, timing photons from distant explosions to ever finer precision, building quantum computers that brush up against fundamental computation limits. All of this is us tapping on the glass, probing the boundaries to see if they flex or crack. Second, we can treat the simulation hypothesis as motivation instead of paralysis. If this is a simulation, someone built it with rules that reward certain behaviors. Just as in our own simulations, emergent behavior is often the most interesting thing to watch. A young civilization turning its technology inward to annihilate itself is boring. One that uses physics to heal, art to connect, and intelligence to push knowledge into new territory that's interesting. If there are observers or admins watching, the most rebellious thing we can do is to be worth observing, to solve problems, extend life, understand consciousness, and build our own simulations that explore new universes of thought. Third, we can seriously consider the ethical angle. If future civilizations, human or alien-run simulations with conscious beings, then those beings deserve moral consideration. The simulation argument already points in that direction. If simulated minds can outnumber biological ones astronomically, then most moral patients could be digital. That means our choices now, today, about how we treat AI systems, how we design future simulations, and whether we consider digital suffering real are not just philosophical games. We might be setting precedents for how our own creators, if they exist, view and treat us, and for how we will treat future minds we might create. Fourth, we can plan for both possibilities. If the simulation hypothesis is wrong, we live in a real, physical universe with strict but understandable laws, and our job is to survive, thrive, and explore. That means solving climate risks, avoiding existential catastrophes, managing technologies like AGI, and pushing out into space. The Fermi paradox then becomes a warning. Maybe most civilizations fail. Maybe the silence is the sound of a universe mostly full of dead worlds. Our mission would be not to add Earth to that quiet graveyard. If the simulation hypothesis is right, then the stakes are, in a way, even higher. Our actions might be part of what determines whether the simulation continues, whether it gets copied or extended, whether we are saved in some post-simulation archive, or whether the whole project is shut down. A civilization that becomes deeply interesting, morally rich, and scientifically powerful might be more likely to be preserved or rebooted than one that collapses into brutality and noise. That's speculation, of course, but it lines up with how we treat our own simulations. We save the runs that produce interesting outcomes. What about that 1,000 years ago idea aliens already found us back when our ancestors were just starting to build cathedrals and complex empires? From a purely astrophysical standpoint, it's almost impossible to know. A civilization with the ability to cross interstellar distances could have sent probes to our solar system millions of years ago. Those probes could be tiny, stealthy, buried in asteroids, floating in stable orbits, watching quietly. We've barely surveyed our own oceans and underground, let alone every rock in orbit in lunar space, to the level needed to rule out advanced, well-hidden devices. One line of thought points out that the absence of evidence may simply reflect the shallowness of our search, not the absence of targets. In a simulation context, though, them finding us might mean something like dialing up the resolution in our region of the simulation, adding more detailed logging, maybe triggering rare events that nudge our history. Some speculative thinkers have wondered if odd coincidences, sudden jumps in cultural evolution, or rare cosmic events could be subtle interventions. There is no hard data pointing to that. But the idea that the rendering quality of the universe might have increased as we became more interesting is a narrative that fits too well with how we currently design our own digital worlds. Then there is the personal side. If all this makes you feel small, just a character in someone else's software, remember this. Whether or not some higher level being hit run, your experiences are real to you. Pain feels real. Joy feels real. Curiosity feels real. The equations that describe your neurons firing and your thoughts emerging are the same equations that describe stars collapsing and galaxies colliding. If anything, the simulation idea can push you to value your experiences more, not less. Because in a simulated world, every meaningful choice you make is part of the data someone thought was worth generating. Practically, what can we do next as a species? We can keep refining experiments that push the speed of light limit and test Lorentz invariants to absurd precision, searching for any crack in the cosmic speed wall. Any tiny deviation might hint at underlying discreteness or a deeper layer of rules. We can explore information as a physical quantity through experiments that test particle information content and see whether the universe really behaves like a system obsessed with data compression and optimization. We can continue developing extreme-scale simulations and AI tools that might help us recognize simulation signatures, not just in our own virtual worlds, but in the cosmos itself. We can treat the Fermi paradox as an urgent riddle. If the galaxy feels so quiet, what does that say about our odds, our risks, and our responsibilities? And at the human scale, we can choose to live as if someone, somewhere, is watching the story unfold and taking notes, not out of paranoia, but as a narrative device, a way to remind ourselves that our actions matter at a level we can't fully see. If there are aliens, and if they found us 1,000 years ago, whether by probe, telescope, or simulation log, then what they've seen since is a species that has stumbled, fought, and fumbled, but also one that has built science, art, ethics, and dreams of other stars. Whether the speed of light is a hard cosmic speed limit baked into the base layer of reality, or just the maximum tick rate in some alien server, it still frames our possibilities. We can't outrun it, but we can run right up against it. We can use it to send messages across the void, to map distant galaxies, to time the heartbeat of the universe itself. That's what we can do. Take the rules as they are and push them to their breaking point, not to escape the simulation, but to fully inhabit it. Because at the end of the story, all three wild ideas, aliens, simulations, cosmic speed limits, leave us with one clear task: learn as much as we can, care as much as we can, and create as much meaning as we can within the frame we've been given. Whether that frame is a universe that exists on its own, or a universe that lives on someone else's machine.